Okay. So we are going to start with the first problem. And I'm going to draw the circuit first, and then we'll decide what we need to do in this problem. So let's say we have let's call this source 1, 10 volt. Let's call this source 2, 100 milliampere. And let's call this source 3, 4 volt, R1, R2, R3, and R4, 20 ohm, 100 ohm, 50 ohm, and 70. Okay, what let's say calculate. Power dissipated in R4. Power supplied by each source. So two things we have to figure out. Okay, guys. So draw the circuit, look at it, think about it, and then tell me how should we calculate the first part? Easiest method that we can employ to calculate the first one. Okay. Well, everyone always says the mesh for some reason, but okay. Let me ask other people as well, and then we'll go back to you. Yes. Wait a minute, you're confusing in two things. You're saying KCL and mesh. KCL and mesh don't go together. KVL and mesh go together. You said nodal analysis. We're talking about only first part right now. Then we're going to move to the second part. Anyone else? Yes, Vanessa. Why do I keep calling you Vanessa and Gloriana? Say it again. Okay. Everyone answered. I have three more answers: Mike, Chris, and Taylor. What do you think? Say it again. Okay. Taylor. So for the first part, you want to apply nodal analysis. Okay, so how are you going to apply nodal analysis? Explain that now. If you are calculating power dissipated in R4 and you said, I want to do nodal analysis, what you're going to do? but that's not nodal analysis. But why do I need that voltage to find the power in R4? If I know the voltage, okay, let me put, you're saying if I know the voltage at this node, let's call this node A, then I will know the current in R4 and R3. Yes.
Wouldn't there be a difference that node then from the other nodes? R2 and R.
You're saying, okay, let me put nodes. So let's call this node B, and or if I go in alphabetical order, let me call this node A, let me call this node B, and let me call this node C. All right. So what did you say, Natasha? Okay. And how are you going to find the voltage of node A and C? They're already given VS1 and VS3. And you guys keep saying, oh, we need nodal. Why do we need nodal? Why don't you apply Ohm's law and calculate the current in R3 and R4? You know the voltages at node A and C. Can't you apply Ohm's law? See, that's the issue here. You guys always jump. You guys don't analyze. You jump to, oh, I need node, I need mesh, this and that, but you don't analyze the circuit. Every time you're analyzing the circuit, you start with the basic. Can I apply Ohm's law? If you can, then you don't have to move forward. You can just apply Ohm's law, right? Ohm's law is the easiest thing. All you need to do is to apply Ohm's law. VS1 minus VS3, which is node A minus node C, divided by R3 plus R4. They are in series. That's the current passing through that branch. And once you have that current passing through that branch, you can easily calculate the power in R4 and in R3, whatever, right? That's something that is lacking there. That's what I'm trying to kind of emphasize since our first meeting, that you guys emphasize a lot more on the solution side without even looking at the problem as, okay, this can be done this way easily. Yes, Natasha.
In my mind, yes, one would affect that.
But yeah, but node C voltage we already know, it's 4 volt. This is 4 volt source connected here, right? This is ground. This is ground. This is, so the voltage difference is 4 volt. That is given to you. You don't apply nodal analysis. You don't apply KCL to the node for which you already know the voltage. Over here, the only node that you don't know the voltage is node B. You know the voltage of node A and node C. If I give you this exam, if the question in exam, I mean, this question is so easy, but I can see that nobody is going to be able to do it correctly. All right. All you have to do is what? Ohm's law. Let's call this I3. Let's call this I1. And let's call this I2. So according to Ohm's law, I3 will simply be what? VA minus VC over R3 plus R2. Okay, let me go ahead and plug in all my values in my Octave, and then we're gonna solve this. You guys should do the same so you can get practice when you're doing an exam. Remember, Octave is, you're allowed to use Octave in exam. Bring your program for the parallel calculation or whatever. I don't really care. Again, those things don't really matter as long as you're doing the correct analysis. That's what matters. And I'll try to give you resistance as variable or everything in terms of variables. Make sure to stick with those variables instead of putting down values like I do in the class. Put everything in terms of variables, and then towards the end you can do calculation, because it's much easier for me to analyze your work if it is written in terms of variables. Okay. All right, so that's 50 milliampere. Is everyone getting 50 milliampere? And once you have this current, this implies power in R4. All right, how I'm going to find power in R4? Say it again. All right, so I3 is squared, because I3 is passing through R4, I3 is squared times R4. $250 milliwatt. That's my problem number one. If I just give you this part, I mean, you can see that this is like not even 2 minutes. But if you don't analyze it properly and you're going to start applying this and that and this and that, and it's going to take half an hour for this question, then you're losing point. Basically, you're losing time. Yes. Okay, let me move up a little bit. Oh, there you go. 100 ohms, 20 ohms, 50 ohms, and 70. Yeah. All right, guys. Now the question is, how are we going to calculate the second part? Power supplied by each source. Who's going to tell me that? Have to find what? Okay, so we have to find VB. Let me, this current is I2 here. This current is IS3. And then this current is IS. So we have to find VB. Okay, once we find VB, how are we going to find power supplied by each source? IS1 is equal to I3 plus I1. Very good. What else? IS3 is going to be? I1 is here on the left side. That's I2. Yeah, that's I2. Okay, IS3 is equal to I2 minus I2 minus I3. Very good. And then what is the last thing that is left? Well, we have the voltage VB, because that's what we're looking for. And once we have voltage VB, that's the voltage across IS2. So remember, to get power from the source, we need the voltage of that source or across that source and the current passing through that source. So we need IS1, we need IS3, and we need VB in order to calculate power of each source. So let's go ahead. And so the only thing that we have to do is apply nodal analysis to find VB. We already know A, we already know C. If you apply mesh analysis, you can. It's going to be longer. It's going to be more complicated. So you're going to apply nodal analysis and get VB. Okay. So for nodal analysis, what is the first step to apply nodal analysis? Apply KCL. So KCL at B. All right. What will be the KCL equation at node B? No? I1 plus I2 plus IS2 all are going towards the node. So I see in the homework, where I graded the homework, I see the same mistake. That you can see, first of all, again, I gave comments in the homework as well. Make sure you show all the currents that you are using in the equations. You show all the currents on the circuit. And I mentioned it last week as well. Make sure you show all the node voltages that you're using in your equations. So you have to have all of those clearly shown on your circuit, and your equations should be according to those direction of currents, according to those node voltages and all those things. So don't write the equation, don't show anything on the circuit. Some of you don't show anything on the circuit, and some of you don't even draw the circuit. And then you guys are writing the equation. I don't know how those equations you're getting, because I need to see those currents, I need to see those voltages to check if your equations are according to the currents and voltages. So that has to be there in your solution, remember that. And based on the current directions that I'm taking, it is simply that all the currents are going towards node B, so all of them will be added together. So these are not something that you should lose points, remember that. These are basic stuff, where like simple things. If you stick with your circuit, you're not going to lose points. I1 plus I2 plus IS2 is equal to 0. Okay, equation for I1. I think Jose and Jose Rudley, they are not here. Okay. Equation for I1. Who is going to tell me equation for I1? Except Yunus. Yunus always tells me equation for everything. Anyone else? Equation for I1. Yes, Natasha. Just for I1. Yes. Okay. Don't say A minus B. Say VA minus VB, because you are putting voltages, right? Yeah. Mm-hmm. Okay. VA minus VB over R1. Good. So simply Ohm's law. Don't hesitate when you're applying Ohm's law. It's simple, right? VA minus VB over R. All right. Equation for I2. Yes, there is. VC minus VB over R2. VC minus VB over R2. And of course, IS2 is given to us, so we'll keep IS2 as it is, or rather we take it on the other side of the equation, because that is a constant value, and it's going to become minus IS2. So again, we know VA, we know VB, the only we know VC, the only thing is VB that we don't know. So we're going to keep VB on one side of the equation and take everything on the other side. So VB, I'm going to take, actually, I should have just kept IS2 on this side, because I'm going to take VB on the other side to make it positive. So let me go back and then just write it down. Plus IS2 equals 0, and then take VB on the other side. So that's going to be VB, and the coefficient of VB will be 1 over R1 plus 1 over R2. And on the other side, I have VA over R1 plus VC over R2 plus IS2. So my VB will simply be VA over R1 plus VC over, and I don't need to write this down, and you don't need to write this down, because we are just doing simplification. So no need to rewrite this, but I'm just writing it for no reason. 1 over R1 plus 1 equals. Okay. So yes, Natasha, yes. That's not a matrix. But it's not a matrix. It's just yeah. I mean, it just VB is a common factor over here, so I just pulled it out. Yeah, yeah, we know VA. All right. Oh, you're looking for VB, right? Okay. So VC is VS3 instead of V. Okay. 10.417. Anyone else got 10.417? Anyone else got this answer? Yeah, resistance value? Yep. Got it? 10.417? Okay. Okay, so now we're going to calculate power in each of these source. Let's just start with IS2 since we know the voltage and current of IS2. So you have VB times IS2 power of IS2 equals VB times IS2. $1.0417 watt. All right, what equation should I write for the power for VS1? VS1 times, say it again, I1 plus I3, or VS1 times IS1. IS1 is I1 plus I3. All right, and of course I1 is VB minus VA minus VB over R1. Or VA minus VB. What was that? VA minus VB over R. So I1 is VA minus VB divided by R1. That's negative 8.33 milliampere. So this power is going to be PVS1 is equal to VS1 times I1 plus I3, 0.4167 watt. And finally, PVS3 is VS3 times IS3. And what is IS3? Yes, Chris, what is IS3? IS3 is what from the circuit? Yes, but what is the equation you said? No, I'm not asking I3 equals. I'm saying what is IS3? No. Sorry? No, IS3. I'm talking about IS3. What is IS3 in terms of the currents that are shown on the circuit? Yes. Guys, this should not be difficult. Come on. Apply KCL. What's wrong with applying KCL on node C? What will be the equation if you apply KCL on node C? Apply KCL at node 3 or in node C. What will be the equation? Yes, Natasha. I'm asking what is IS3 in terms of KCL. I'm not asking what VS3. VS3 we already know. What is IS3? I2 minus I3. So why it is so hard to apply KCL at node C? Two currents are going towards node C. What are those two currents? IS3 plus I3 equals the current that is going away from the node. What is that current? I2. So why it is that hard? Current going towards the node is equal to current going away from the node. All right. What is I2? I2 is what? How are we going to calculate that? Okay. VC minus VB over R2. Negative 0. Yes, go ahead. For the power in VS1? IS1 times VS1? Yeah? IS1 is I1 plus I3. What is I3? 250 milliwatt. Sorry, 50 milliampere. I3 is 50 milliampere. So that's going to give you a positive current. And again, if you're putting them in terms of variables, you don't really have to worry about that because they are there in terms of variable, right? So I'm just putting I1 plus I2 or whatever. It's going to fetch those values. If it's a negative value, it's going to show you negative value. If it's a positive value, it's going to show you positive value, right? You don't really have to worry about that. If it comes out to be negative, that means the source is going to be absorbing power. Otherwise, it's going to be supplying power. 1667. So I'm just going to write down 2. And so this is going to be PVS3 is equal to VS3 times I2 minus I3. And that is a negative power. So negative 0.5667. 0.5667 watt. Negative power supplied is positive power absorbed. And once again, make sure you do it on your side as well. So in case my answer is incorrect, then I know that there's another answer and we can check. Either mine will be correct or yours will be correct. Don't just copy what I'm doing. Make sure you do it on your side. And again, highly advise you use Octave, use MATLAB. Even if you're using calculator, don't use numbers. Assign variables. All of the calculators, I think they have, you can assign variables, numbers to the variables. Use variables, guys. It's gonna be, your life is gonna be much easier because it's waste of time to keep crunching number anytime you're doing the calculation. Same number, enter again and again and again. There's more chances of making a mistake, making an error. Learn how to use variables. All right, question about this. Now, it's perhaps one of the easiest problem that you can see, and still I can see that the Ohm's law is not clear, KCL is not clear. Everyone just want to go for KVL for some reason. So I don't know what's going to happen in the exam, but we'll see. And this is again something that is not new to you. All of you have done these things. Some people did it recently, some people did it a long time ago, irrespective. Everyone, these are the basic concepts. Everyone, you have learned these concepts basically. Okay, we're gonna move on. If there's any question, make sure to ask. I'm gonna just pick a few problems from the book, and then we're gonna solve those problems. Let's see. And if you have a problem that you want me to solve, then let me know. You can solve those problems as well. Okay, let's solve this problem real quick. Let's go to the new page. Picking up this problem from the book, old edition, but it's still from the book. Okay. Power supplied by the dependent source. That's what we need to figure out in this problem. All right, who's going to tell me how we're going to figure out what is the power delivered by the dependent source? What do we need to know? Yes. All right, if we know Vs, then how are we going to calculate the power supplied by the dependent source? Resistance of the dependent source. What is the resistance of it? Yeah, determine the power supplied by the dependent source. Okay, so what will be the equation basically? If I want to write down the equation to calculate the power of the dependent source, 0.1 Vs times 0.Vs square. Okay, well, Vs times ID, because Vs is the voltage across the dependent source. Vs times ID, and ID is 0.Vs. So 0.1 Vs square is going to be the power simply supplied by the dependent source. Okay, to calculate the value of Vs, what should we do? Hmm? Well, that's Vs. That's what we're looking for. And how are we going to set up that equation? Mesh analysis. How many meshes do we have? Anyone else? Yeah, one node. The voltage of that node is Vs. So why are you gonna even go to the mesh analysis when you only have a single node on top, and that's the voltage that you're trying to find out. That's the voltage Vs, the node voltage on top. Yes. You cannot combine current sources. You can combine resistors if you want, they're in parallel to each other. You cannot combine the current sources. You just apply the nodal analysis on the top node, or apply KCL nodal analysis. That's all you need to do. It's a single node on top. That's about it. And that's the voltage Vs you're looking for. Single node, and you need to know the voltage of that single node. Let's say this is I1 and this is I2. This is node, let's say we just call it node S with the voltage Vs1 or Vs, sorry. KCL at S. All right, what will be the KCL equation? Say it again. I what? ID? ID, okay. ID equals what? Say it again. ID. IS1. Wait a minute. You're saying ID equals IS1 equals? You're putting two equal? Well, how are you going to put two equals? ID plus IS1 equal? All right. So that's the correct equation. All right. Okay, so ID is 0.1 Vs. Remember, we are trying to figure out the voltage, not voltage Vs. So we can put everything in terms of Vs. IS1, we know the value. No need to do anything with that. All right, what is I1? Vs over what? What is I2? All right, and IS2 we don't know. All right, so the equation is in terms of Vs, and that's what we are looking for. So bring Vs on one side of the equation. 0.1 minus 1 over R1 minus 1 over R2 equals IS2 minus IS1. And from that, we can calculate Vs equals, let's go ahead and do that. What do I have? IS1 is equal to 5.6. R1 is 18. R2 is 9. And then IS2 is 2. So Vs is equal to IS2 minus IS1, IS2 minus IS1 divided by 0.1 minus 1 over R1 minus 1 over R2. And that gives us 54 volt. Therefore, power ID, which is equal to Vs times ID times 291.6 watt. Yes. Okay, look at the direction of current and tell me what will be the KCL equation. You tell me. Don't worry about, we're trying to find what. I'm asking you what will be the KCL equation from the circuit at node S. Don't tell me you understand what or you don't understand what. Just tell me what is the KCL equation, right? What is the basic of KCL? If you have a node, how do you write the KCL equation for that node? Okay, so what is KCL? Okay, go back. What is KCL? Define KCL. No. KCL is Kirchhoff current law tells you what? At a node, what does it tell you? If you are looking at a node and applying KCL, then what does it tell you? Okay, and what is the relationship between those currents? No. You're saying current going towards the node and leaving the node. What is the relationship between those two currents? What is the relationship between the currents going towards the node and leaving the node according to KCL? Currents that are going towards the node equals current going away from the node.
Yeah, I have a thing too.
So now apply KCL at node S.
So ID, so going towards node is ID and IS1.
Okay.
But when I1, I go towards it as well.
What is the direction of I1? Going away or going towards?
I see it's still downward, so it's like
Thank you. Okay, a lot of work needs to be done, guys, please. A lot of work. I mean, if you're struggling with this basic KCL, you guys need to catch up, please. Otherwise, you're going to fail the class. I'm telling you. At this time, you are going to fail the class if you're struggling with the basic concept of Ohm's law and KCL. As it's fourth week and just we're doing review, and there's still a struggle with just the basic concept of current going towards, current going away. I have not seen this struggle before whenever I taught this class. So please, you guys have to work really hard in order to do good in this class, please. Yes, Rudley. No, I chose the direction. You can choose any direction, but you have to write the equation according to that direction, right? Yeah. The only direction that are given to us is IS1 and ID and IS2. 3 currents are given to you. Now the blue one, I chose those directions. But even if those directions are given to you, like these going away, then when you write the equation, it's going to be this. If you choose it that it is going towards, then you're gonna move those currents on the side of the equation which are going towards. So just this, so the problem looks like this. The problem is in front of you, right? Whatever the problem is, I'm saying, okay, I'm choosing the current going away, write the KCL equation according to that. That becomes your problem, right? So once that becomes your problem, you're going to write the KCL equation according to the current that I'm choosing or you're choosing. As simple as that. Doesn't matter what books you're choosing. If a book is choosing in the opposite direction, I can choose in the opposite direction, and I can write the equation according to my direction, because at the end, if my direction is incorrect, it's going to be negative, right? But you have to apply the KCL correctly. You have to apply the KVL correctly. You have to apply the Ohm's law correctly, but all according to the direction of currents, the direction of voltage source, and all those things. If you just write down incorrect equation based upon, whatever, then your results are going to be incorrect. If you have any question at any time, or if you want me to solve a question, if you are solving a problem, you are struggling with it, I can solve that problem. So yes, yes.
One thing that I thought of doing was also doing current divider for this, but then
Why?
so it's and this is the reason why. So I was just thinking one of the homeworks didn't have a dependent source on it,
Okay,
but I was able to use a current divider that looked similar to this particular current source.
okay, all right.
When you said no, like why would we do that? But so you think that would have been a bad approach?
Yes, it would be a bad approach. It's going to be a complicated approach. You'll have to think a lot more to do whatever you are trying to do. This is the easiest approach, since we don't, all we need to do is apply KCL and Ohm's law and basically nodal analysis and find the value of PS. That's what we're looking. That's what, have the goal set up, right? What you're looking for, right? Once you have that goal set up, once you're very clear, this is what I'm looking for, because if I do this, I'm going to get my results based on that. Once your goal is set, then you think about how I'm going to get that goal, what I'm going to use. To start with the Ohm's law, because that's the easiest thing. If the problem can be solved using Ohm's law, you don't need to go further beyond, right? You just apply Ohm's law. That's the basic thing. If it cannot be solved using Ohm's law, then go to KCL, apply nodal if necessary, KVL, apply mesh if necessary, source combination, whatever. But don't forget that the basic thing, if you can do Ohm's law, go for that always. And then voltage division, current division, whatever you want to do, it's all valid. And really, it all depends on the circuit, you know.
That's what I was asking.
Yeah. Yeah, I don't even think about current division or something. If I see, oh, this is very easy to solve, I just need to solve for this node voltage, and I can write the equation for the node voltage in one line, I'll have my answer. So why even think about more complicated things? You know what I'm saying? It's the easiest thing that you want to do, that's what you want to do. Yes, Chris? Yeah, I will. I'm just going to do one more, and then we're going to take a break, and then we'll keep on going until 11:30, of course. Okay. All right, let's see. calculate the power supplied by IS4. Meantime, I can enter the values. Oh, what happened here? All right, guys, if you copied the circuit, let me know what is our goal in this problem. That is to find what in order to find the power supplied by the source IS4. What exactly we're looking for. First, establish that, and then how we are going to find that. We are looking for the voltage across IS4. Very good. So that's what our goal is, so that we can calculate the power supplied by IS4. This is what we are looking for. VS4. Okay. What is the easiest method you think to find that VS4? Say it again. Okay. How are you gonna apply Ohm's law to find that? It's not a single loop. Say it again. Okay. And do what? And how are you going to find that voltage drop? Yeah, but VS3 is the voltage across that voltage source, not the voltage at the node between R2 and R4 and VS3. That's not the voltage VS3, because you have a 90 ohm resistor at the bottom R3. Okay. If we know the voltage at that node, then definitely we will know what is VS4. So we need to know the voltage at this node. Let's call it node A. Now, a couple of ways we solve this problem, and both are very easy. Of course, KCL and nodal analysis is the first one. What about mesh? If you apply mesh, which is your favorite, if you apply mesh, how you can solve it? One loop, exactly, because the right loop, we already know that the current is IS4, so we don't need to apply mesh in that. We can apply mesh on the left loop and find the current. And once we find the current, then of course we can apply KVL in the right loop to get VS4. So again, your call, whichever way you wanna go. Both of them are very easy, but you have to establish, of course, that how you're going to. Your goal is to find VS4. And you can find VS4 if you know VA, or if you know the voltage across basically VS3 and 90 ohm, which is VA, whichever way you want to want. Since we have used KCL and nodal analysis a couple of times, let's go ahead and solve this using the mesh analysis. And let's see, our mesh current here is I1, and of course our mesh current here is IS4. So we don't need to apply the mesh analysis. on the right loop because the current source is in the exterior branch. So KVL in the loop with current I1. All right, what will be the KVL equation if I apply KVL in this loop? Who's going to tell me? VS1 plus VS2 no, not plus I1 R1. Minus VS3, okay, keep going, equal, all right, nope, plus, same direction. That's the KVL equation. Anyone has any question about this KVL equation? Make sense? Both are going in the same direction in the common branch, yeah. That's why we put plus. Make sense, everyone? Okay. I1 is what we're looking for, and I1 is what we're gonna get. So I1 is equal to VS1 plus VS2 minus VS3 minus IS4 times R3 divided by R1 plus R2 plus R3. Negative 6.667 milliampere. Let me know if you get the same. 10, 5, 7, and IS4 is 180. R1 is 10, R2 is 50, R3 is 90, R4 is 20, R5 is. Let me know if this answer is correct or incorrect. That means our assumed I1 direction is opposite to the actual IS direction is opposite to the assumed direction. But that's fine. Magnitude is the same. Yes.
So it's
All right. So write it down in terms of sign. Maybe you have learned in terms of sign when you are writing down. So start with VS1. You're entering in the negative side. So negative VS1, negative VS2. Now when current will enter into resistance, it's going to be positive negative. Plus I1 R1 plus I1 R2 plus VS3 plus I1 R3 and then plus IS4 R3 is equal to 0. Right? Once you write, so write it down whichever way you learn, write down the equation. And then kind of move it around to see if you get the same result. So sources basically are what I'm writing is sources on one side, and resistor will always drop, the voltage. So all the drops are on the other side. Now my VS1, VS2 are in the same direction, so both of them added. VS3 is opposite direction, so I subtracted it. And then on the right-hand side are my all drops in the resistors. So all of those drops will be added together. And of course, my direction of current in both loops are such that it is flowing in the same direction through R3. So both currents are going to be added together, passing through R3. All right, got the same result, different result, same result. Okay. All right, now we know what is I1. So my question is, how are you going to figure out what VS4 is then? Because your job is not to find I1, your job is to find VS4. I1 will help you find VS4. We can write another KVL on the right loop, on the rightmost loop. That is correct. That's a good answer. So if we write KVL equation for the loop with current IS4. All right, what will be the KVL equation? What will be the KVL equation? Go ahead.
Sorry, I was catching up.
IS4. Yeah. Lazaro.
Yeah, VS4 minus.
Okay. Okay, good. IS4. All right, what else? All right, what is missing in this equation? So far, this equation is correct. One part is missing. What is missing? Mike, what do you think? I1 R3 plus I1 R3. Yeah. Because in R3, two currents are going, I1 and IS. All right, so now we know how to calculate VS4. So let's go ahead and do that. So our equation is VS4 minus VS3 equals IS4 R3 plus R4 plus R5 plus I1 times R3. And from that, let's calculate VS. VS4 equals IS4 times R3 plus R4 plus R5 plus I1 times R3 and then plus VS3. 27.4 volt. So therefore, power IS4 is equal to VS4 times IS4 2.74 watt. All right, let's look at now. We solve a couple of problems using Ohm's law, nodal analysis, mesh analysis. So let's move on to the next topic. And let's see. Of course, current division, voltage division, it depends on the circuit. You can apply current division, you can apply voltage division as well, where you need it to apply. All right, what is this? Okay, let's solve this problem. Should be a voltage source, of course. Okay, let's see what they're asking. This one. Assume R3 to be the load resistance. Okay. Assume R3 to be the load resistance, determine Thevenin equivalent circuit across. All right, so to find the Thevenin equivalent circuit, what is the first step that we need to do? Well, of course, we have to find VThevenin and RThevenin. What should we do to, let's say, to start with V open circuit, VThevenin? We're going to remove R3, of course. So our circuit is going to become so V3 is basically V open circuit. I'm sorry. Yeah, R3 we are assuming to be R load. Yeah, that's what I wrote down. Assume R3 to be R load. So we have to find the open circuit voltage between that resistance or those nodes, and call them node A, B, whatever you want to call them. Node A, node B, C. V1 is here. V3 is VC minus V3 is the difference between the two voltages, VC and VA. All right, guys, what should we do? What's going to tell me? Okay. What do you want to say? Hmm? Okay. How are you going to apply? How are you going to apply mesh on this one? Both. Okay, and that is going to be the difference between the two currents. Okay. So that's one way to go. We can write two equations, or it's going to be actually one equation only. All right, VB. If we apply KCL at VB, what will be the equation of KCL at node B? Say it again. Okay. I mean, in the KCL equation, you're putting current and voltage together. Huh? But you cannot add current and voltages together in the equation. You know the current here. Anyone else? Say it again. All right. Anyone else? ID1 plus ID2 plus IS1 all are going towards node B. ID1 is going towards node B. ID2 is going towards node B. It's not going to go here. It's open circuit. So this current is going to go here. And IS1 is going towards node B. Okay. The only thing is we don't know these, because V1 is the difference between VC and VB. We don't know VC. And then likewise, we don't know VA. V3 is the difference between VC and VA. So let's see. But the book doesn't call for this. I changed this problem. Book didn't call for this. So let's see. But we cannot solve the problem if our number of equations are less than the number of unknowns. You know, IS1, ID1 is 0.02 V1. V1 is this. Now V1 is ID2 times R1. Okay, let's write this down. IS1, let's see if this works. IS1 plus 0.02 V1 and plus ID2, which is 0.2 V3 equals 0. IS1 plus 0.02. Actually, we can keep ID2. We don't have to put that. Let's try this. I think this may work. We write everything in terms of ID2. So 0.02 V1, and V1 is what? ID2 times R1, right? Because ID2 is going through this current R1. So ID2 times R1 is V1. So we can write everything down in terms of ID2 and find ID2 first, and then we can find other things. So 0.02 times ID2 times R1 plus ID2 equals. How about this? Make sense? because again, if we use the nodes and all those things, then we will have more equations. We have less equation and more unknowns. So let's solve for ID2 first. Therefore, ID2 0.02 R1 plus 1 equals negative IS. So ID2 is, let's calculate the value of ID2. Okay. What are my values? R1 is 2, R1 is 2, R2 is 3, R3 is 5, and IS is 10. So ID2 is negative IS1 divided by 0.02 times R1 plus IS. It's not it's not IS. It's no, I put IS1. I took IS in, so it's IS, not IS. That's the variable I took in the first circuit. I'm just gonna stick with that. IS. S and IS. Okay. Negative 9.6154. Negative 9.6154. So that's my ID2. Okay, so now we can calculate ID1 since we can calculate V1, since we know ID2. And we can calculate V3 as well, what we are looking for actually. So V1, actually all we need to calculate is V3 because that's the open circuit voltage we're looking for. We just calculated from the relationship. ID2 is equal to 0.2 V3. It is 44 point. Negative 48.07 in this direction. Yes. R1 is 2 ohms. To find our Thevenin, what should we do? Okay, we can short those two terminals. And once we short those two terminals, V3 is going to become 0. That means this ID2 is going to become 0, the value of that ID2. That means the current source, we can, if the current source value is 0, we can open circuit it. We can eliminate it. We can open circuit it. So that current source is going to go away if we short the terminals C and A. Let's do that. The other thing we can do, of course, is to apply a test source over here and remove this IS and then find the test current. That's also we can do. Let's see which one is going to be easier. If we apply a test source over here, we will know the voltage of that test source, and then ID2 depends on that voltage. So we will know the value of this ID2. We can eliminate this. I think short will be better. I'm sorry? You eliminate the independent sources, not the dependent sources. You eliminate the independent. So only this source is going to be open when you apply the test source over here. Let me see if that is going to be easier. Yeah. These two current sources are going to create a problem because they're in the same loop. Instead of voltage source. Yeah, let's short it. Let's see. Oh, if we short it, this will be eliminated basically. So you're gonna have R1, R2, short circuit here, and then these two sources here. Let's see how would that go. Let's short IS and no, sorry. Let's short terminals A and C and find I short circuit. And the source that will be eliminated is ID2. Since V3 will be 0. That's going to be your circuit. This is R1. This is R2. V1. That is going to be your circuit. And you can find the short circuit current. Whichever direction, doesn't matter. 0.02. Okay. Same circuit, different topology, perhaps easier to understand. So the voltage V1 is basically the voltage across R1 and R2 because both of them now appear to be in parallel between the two nodes, this node and this node A. Both are connected between node A and node. Yes.
Be arbitrary.
No, not arbitrary. V3 is 0. That depends on V3.
Okay, okay, never mind.
0.2 V3, right? All right, how do we solve this thing? Make them a little more complicated. So again, the goal is to find the short circuit current in passing through. I would say here. This is I short circuit. Right? But I mean, this has the opposite direction. Negative at the bottom, positive on top. Negative at the bottom, positive. According to this, positive is away from B. Positive is here, negative is here. So we can do ISC in the opposite direction, actually, whichever. All right, who is going to tell me what should we do? Yeah, the current is going to be divided in the two resistors, whatever the current is flowing, because we can take the equivalent of those two resistors. The voltage V1 is going to be the same voltage across the two resistors. V1 over R2, right? Negative. So you want to apply basically, and V1 of course, is VA minus VB. That's your V1. So you want to apply KCL at node B and node A. Let's try. Okay. So one ISC. Okay. IS going towards and I1 and ISC going away. Actually, we can just find V1 from this, right? Because I1 is what? I1 is, what is I1? Negative V1 over R2. If I'm taking V1 direction, this. Because of course, when I1 enters here, positive voltage is going to be on the right side and negative voltage is going to be on the left side. But since I'm taking I1 in the opposite direction, then that simply becomes negative V1 over R1. And likewise, short circuit current is going to become, once again, negative V1 over, this is R2, sorry, not R1, over R. And from that, we can find the value of V1 I source divided by negative 12. Therefore, I short circuit, which is negative V1 over R1 is 6 volt, 6 ampere, sorry. Which implies our Thevenin will be V open circuit over I short circuit. And of course, we're going to take the magnitude 48.07 divided by 6. .01 V Thevenin is what, 48.07. That's going to be our Thevenin circuit. It's a little complicated problem, so yeah. Yeah, polarity you can switch. It doesn't really matter because what you need to know is what is the Thevenin voltage source and what is the Thevenin resistance. The way you're connecting the resistor, it doesn't really matter if you have, because the current is going to flow wherever the positive side of the Thevenin source is, right? You cannot expect this problem, of course, for quiz or exam, because that's a little complicated. Let's find another Thevenin, but a little easier problem. Let's see. Okay, we'll start with the easy Thevenin, and then if we have time, we're going to do one more with. So we're going to do one without the dependent and one with the dependent. That was problem number 4, I assume. Problem number 4. Okay, so let's do problem 5, and then hopefully problem 5 is easy. So we'll have time to do one more quickly. Okay, so there's the circuit. Now you guys are going to tell me what should we do to find the Thevenin, or to find the load resistor that will receive the maximum power, and how we're going to calculate the value of that power. 7 exponent -3. Give me 1 second. Let me write down all of my 2 exponent 3 or 5 exponent 3 equal to 1 exponent. Okay. All right. So what do we need to do? We want to find the equivalent resistance where? So equivalent resistance looking into which ports? Okay. So what you're trying to say is we find the equivalent resistance looking into nodes A and B, which is the Thevenin resistance basically. Right. Okay. And that why we are finding that resistor? So, well, no, not that resistance value is going to give us the max power. If we connect a load, between A and B, which is equal to that resistance, that load is going to receive the maximum power. Resistance cannot give you the power. Remember that. That's a Thevenin resistance. Okay, so the value, the load value, which is equal to the Thevenin resistance, is going to be the one that will give you the maximum power. Very good. That will receive the maximum power, not give you. Resistance cannot give power. That will receive the maximum power. Okay, and how are we going to calculate the value of that maximum power? What are we going to do? We need voltage where? Okay, and that voltage is equal to, what is that voltage? That's the Thevenin voltage. Very good. So you establish, that's the first thing. You establish what you need to do. So you need to first figure out what is the Thevenin resistance. Basically, you are Theveninizing the circuit between nodes A and B. So R Thevenin between A, B, or R equivalent, which will be R Thevenin. Okay. So once you remove the two sources, I'm not going to redraw the circuit. Once you remove the two sources, what will be the combination of resistors that you can make such that you get the equivalent looking into nodes A and B? Okay. All right. R1 parallel to R2 plus R3. Okay. Let's do this. R Thevenin is R1 R2 plus R3. 2.428K. 2.42. See if you get the same one. K. 2.428K. Right? Okay. All right. And now to find the Thevenin voltage, which is the open circuit voltage between A and B. All right. How are we going to find that? Who's going to tell me? What should we do to find that voltage? Yes. How can you add a voltage and current together? You
So,
can't.
It would be IS2 minus
R2 and R3 are not in parallel. All right, Mike, what we should do to find the voltage, open circuit voltage, which is the Thevenin voltage? That is the voltage that we are looking for, yes. How are we going to find that voltage? You're saying apply what? Well, there is a node at IS2 right here. I know. I mean, that's the node, yeah. And that is the same voltage as A because again, R3, no voltage will drop in R3. So it's the same node as node A. So how are we going to find the voltage of this node? What you're going to apply? Any suggestions? Okay, you apply KCL. Let's assume that current here is I1, this is IS2, and let's assume current here is I2. So what will be the KCL equation? No. Yeah. I1 plus I2 plus IS2 equals 0. Okay. All right. What is the Ohm's law? If you want to write down I1. Yes. Come on. Yes, there is. Uh-huh. No. Hmm? VS1 minus VA over R1. Yeah. VS1 minus VA over R1. All right, and I2. Say it again. I2. This is I2 right here. This is I2 going in R2. Rudely, what will be I2? There's a little bit of issue over here. Look at the direction of current. Yep. So 0, assuming this is ground, 0 minus VA over R2. So minus VA over. And of course, IS2, we already know the value of IS2. I'm going to take it on the other side of the equation. Or actually keep it on one side and then take the other things on the other side of the equation because VA is negative. So I'm going to keep IS2 is 7 milliampere. So VA will be equal to, take VA on the other side. The denominator is going to be 1 over R1 plus 1 over R2. And then you're going to have VS1 over R1 plus IS. So VA is VS1 over R1 plus IS2 divided by 1 over R1 plus 1 over 12.143. 12.1. And this VA is, of course, Thevenin equivalent voltage because VB is grounded. So what Thevenin circuit? RL is R Thevenin for maximum power consumption. And you can calculate the power. I don't want to go and do the power since we don't have much time. I don't want to do at least one more problem. Any question about this? This is the easier version of Thevenin in which there is no there's no dependent current source. All right, let's do the last problem. That's going to be problem number 6. Let's see if I can find a problem. Okay, let's do this problem. I don't know if we did this or not. Anyways, I don't remember exactly. Not a very hard problem. It's rather simple, and you can expect me to give you a simple problem. You know, you cannot expect me to give you a hard problem because I can test your knowledge just with the simple problems. I don't have to give you any complicated problem for exam. All right, and let's see. Simply, let's do determine the Thevenin circuit across A, B, and calculate the power in a 1 kilo ohm load connected. All right, guys. So the first step is to find the Thevenin equivalent circuit between A, B, and then we're going to connect a 1 kilo ohm load to the Thevenin circuit between nodes A and B and calculate the power in that load. For Thevenin, of course, we need Thevenin voltage and R Thevenin. And since this one has dependent source, we cannot eliminate the sources in order to calculate R Thevenin by the combination of resistors. Make sure don't do that. If you do that, your result is going to be incorrect. So what we should do first, what we're going to find first in here. We can find VThevenin, we open circuit VThevenin, and then we can find R Thevenin either by shorting A and B or by applying a test source between A and B and removing the Vs. So there are two methods to do that, but both methods require you to at least find VThevenin using circuit laws. So let's go ahead and find VThevenin first. Okay, from the circuit, VThevenin, which is V open circuit, which is VAB, what do you suggest we should use to find VThevenin? Any suggestion? If you're solving this and you have to find V open circuit, VAB, what you can apply? Okay, and which node you're going to choose to apply nodal analysis? On top of R1? Okay, and if you do that, then you have two currents, one going through R1, one going through VS, but how are you going to write down about that current that's going through VS? I mean, you can use super node if you want. It's just going to make it a little more complicated. Yeah, there's a node on top of R2. If I have to do it, I'm just going to apply mesh on the loop with Vs because we already know the current in that mesh, which is ID. And once I know the mesh current, then of course I know R1, which will be mesh current times R1, right? Then I can find the open circuit voltage. So if I'm using this, I'm going to apply mesh analysis. Call this current I1. This current we already know is ID. KVL in the loop with current I1. Okay, so tell me what will be the KVL equation for this loop. Okay. Okay, minus Vs. Plus minus sign. Sign, what will be the sign of? Huh? Plus, okay, all right. Plus I1 R1 plus I1 R2, okay. Very good. And A equals 0, very good. So I'm going to write down, instead of negative Vs, I'm going to keep Vs on one side. Vs is equal to I1 R1 plus R2 plus ID R2. Okay. And of course, ID is 0.02 V1. And what is V1? Say it again. I1 R1. Therefore, I can write down Vs is equal to I1 R1 plus R2, and then I'm going to put this I1 R1 here, V1. That's going to become 0.02 R1 times R2. And from that, we can figure out what is the value of I1. R1 is 10K. R2 is 20K. Vs is 1 volt. And that's all I need. Oh, I didn't type. Go ahead. Oh, I did type. Okay. All right. So I1 is equal to Vs divided by R1 plus R2 plus 0.02 times R1 times R2. Well, it's a small current. 2.48 exponent negative 7, so 0.248 microampere. Anyone got the same result or not? Or 248 nanoampere? Let me check if my result. What is Vs? Vs is 1 volt. R1 is 10K. R2 is 20K. 0.02 V1. So ID is 0.02 V1, and V1 is I1 times R1. I1 times R1 plus. Okay. Oh, well, it is what it is. 248.14 nanoampere is what I'm getting. See if you're getting the same result. Got it? All right. Therefore, Thevenin, which is equal to V open circuit, which is equal to V1 I1 times R1. Thevenin is I1 times R1, which is 2.48 millivolt. 2.48 milliohm. So that's our VThevenin. In order to get R Thevenin, what should we do? What will be, now analyze both method. Anytime you're trying to find out R Thevenin, analyze both method in your brain as either you short circuit A, B, is that going to be easy? Or if you apply a test source and eliminate the independent sources, is that going to be easy? If we short circuit A, B, what's going to happen to the circuit? V1 is going to become 0, which means that ID is going to be eliminated. ID becomes 0, that means it will be open circuit, it will be eliminated. So I think that may make the circuit much simpler because R1 is going to be gone, ID will be gone, and you will have only one loop with VS, R2, and short circuit. That's going to be much easier. So let's do that. To calculate R Thevenin, short A, B terminals, and find I short circuit. V1 will become 0, implies ID will be 0, and R1 will be eliminated. So our circuit is going to become simply this circuit. A, B, positive, negative, VS, R2, and we are looking for I short circuit. Becomes much, much simpler, just Ohm's law. ID is gone, R1 is gone because this becomes short, so this and this one. So I short circuit will be equal to VS over R2. $50 microampere, which implies R Thevenin, which will be V open circuit over I short circuit, or V Thevenin over I short circuit. $49.62 ohms. Therefore, the Thevenin circuit and your 1 kilo ohm resistor. Who's going to tell me? What was the Thevenin value? 2.48 millivolt. Who's going to tell me how we're going to find the power dissipated in the load resistor that is connected? Because that was the question, that we have to first Thevenin, find the Thevenin equivalent, and then connect a 1 kilo ohm resistor to find the power. Calculate the power in 1 kilo ohm load connected between A and B. So we connected a load of A between A and B, 1 kilo ohm. How are we going to find the power? Okay. Okay. Voltage divider to find the voltage across. All right, so VRL, and then square that voltage and do what? VRL is equal to V Thevenin times RL over RL plus R Thevenin. VRL is equal to V Thevenin times R 1000 times divided by R Thevenin plus 1000. 2.34 2.36 millivolt. Therefore, power in RL is equal to VRL square over RL. .58 nanowatt. 5.58 nano. And this will wrap up our work for today.